Uh-huh. So on worksheet 7B, there's a matching activity where they give you an original graph, f of x. Unfortunately, it's super tiny and very hard to read. So the first thing I'd like to do is point out some ordered pairs that I'm going to say I can see, but the answer is actually you can see them because I can't see them. For instance, this little max right here, you want to tell me about where this max is located? Best estimate for it, guys. Does it look at, like, is it about -1, 2? I don't really know.
I would say.
Okay. I really can't see it. I'm not playing coy here. All right, what about this little minimum dip?
2, -12.
All right, we'll go with it. So again, it's an estimation. We can't really see. It's kind of hard to tell. But on the original function, those maxes and mins are going to be really important to me when I'm trying to figure out how everything was transformed. So without looking at the graphs themselves, I want you guys to talk to me about different transformations that occurred on these different choice selections. So let's hold off on A, and let's look at C first. So can you guys look at choice C? When they throw a negative in front of your f of x, do you remember what that does to your function, what we call that transformation? It is something, yes. R. It's a reflection, but you got to be specific. What kind of a reflection? Good. Reflection over the x-axis. So can you talk to me about choice B then? What happens when you throw a negative inside of your function?
Reflection over the y.
Very good. Reflection over the y-axis, which is a new one for us. A little weird. How about, let's look at letter D. What does that transformation mean when you throw a 3 in front of a function?
That means that it's stretched.
Okay, I heard a vertical stretch of 3. I can't spell. Okay. Stretch. Stretch. There we go. Of 3. Let's not talk about the absolute value bars. That'll be obvious in a minute what it does to the graph. What about letter F, where it has a -5 off to the side like this? It will transform it somehow. That's what I'm looking for. Is it shifting it?
Oh, 5 to the left.
Well, it's outside of the function. So it would be a vertical shift of down 5. All right, and then let's put a couple thoughts together here on this first one. Choice A has a negative in front of the function, which applies first, and then it has a +4 at the end of the function. So there's 2 transformations here. What are they?
Reflection over the x-axis.
Yep, reflection over the x-axis, and then up 4. And I like the order in which you guys gave me those transformations, because we learned yesterday that for the reflection to happen after the up 4 shift, that would change everything very drastically and wouldn't be correct. So it has to be a reflection first, followed by an up 4 shift. Okay, it is time to start matching. And actually, one of the first questions here is probably the trickiest one. Not the first one. This is the new guy. This is the original guy. And remember, you guys identified a rough estimate for where those maxes and mins were. So this guy, the minimum is now located at, man, I can't see that. Is that like -3?
Yeah.
-1, -3? I don't know. I can't really see. For the maximum, excuse me. And then this minimum is down here at, I don't know.
Yeah,
2 comma -17, you think? I really can't see that. Man. Can't read that. Anyways, it's lower. So anyone think they identify which transformation occurred there? Because I don't see any other weird things happening. It doesn't look to be reflected. But it definitely was shifted down.
Down.
So which choice is that? Wasn't it at -12 originally, and now it's at -17, we're thinking? Down 5. That would be choice F.
Wait, what?
We weren't sure on the estimation for the points originally, but everything seems to be shifted down 5. And that's the only one that makes sense. Here's my promise to you guys. If it's on a test, I will make it A, legible, like you can read it. And B, I'll make sure things are labeled so there's no hemming and hawing over, like, is that at 3 or is it at 2? You know, you'll know. So this next one. Compare the original function to this new transformed one. Anyone think they noticed some things that happened? So you're seeing a reflection?
Yeah.
Okay. Cool. And you think it's B?
No, I don't think it's B.
Oh.
How dare you?
All right. Well, here's how we're going to tell the difference. We're going to figure out where the ordered pairs are and whether the Y's were simply reflected or something a little more exciting happened. So, like this guy, for instance, the original one was way down here at negative 12. And if it was just simply reflected over the x-axis, it would now be up at positive 12. Is it?
No.
Ah, so it was reflected, but then something else happened. Feels like it came...
Bamboozled me. I thought it was still... Never mind.
So this is a weird one because a lot of kids are going, but wait, that doesn't make sense. If I was at now positive 12 and then the only option here is to move up 4 units, that wouldn't match. But remember the order in which the transformations were applied to the function. They reflected it first. Man, I can't read that. Oh, it does make sense. Ignore me. Forget what I just said. Because I thought that was a 6, and that's a not. It's like a 15 or something, isn't it?
12?
I don't know. What is this number up here?
I
I can't read that.
don't know.
Okay. So was it reflected and then moved up 4? Cool. So that would be choice A. Man, I've never felt like I needed bifocals more than doing this worksheet. I have one pair of bifocals that I hide at the bottom of my desk somewhere because I refuse to wear them. All right, let's check out number 3. That one's a little more obvious. If you just kind of step back and look at 3,
D.
something has happened to that. It's been vertically stretched, I'm hearing. So yes, that would be, the only choice would be D.
Number 4 is E.
Okay, so 4 is the weird one. Good job, Cameron. Did you watch our lesson?
No.
Oh, you could have lied to me. So the absolute value around the function states that you take all of your negative pieces and you reflect them up to the positive land. So that's exactly what happened. So that's choice E. And then, what else we got here? Number 5. Whoa. Now, here's what I noticed about number 5. This minimum point is still just as low as it was before. It's still down at negative 12, but it's been shifted over to the other side of the y-axis. Therefore, it's B, reflection over the y-axis. Clearly, it is B. Oh man, I don't know. Okay, where's this guy? Is that up at 12 now? What used to be located at negative 12? So what are you thinking? I'm hearing C. Very good. Is that the end of it? All right, cool. I'm going to give my eyes a break. Could you find the next worksheet? It's piecewise functions. It's graphing. When you guys walked in, you might notice you picked up 2 things. You picked up a piecewise packet along with a piece of graphing paper. You must do your homework tonight from the textbook in graphing paper. Very, very important. I preferred yesterday's homework to also be done on graphing paper, so if you have yet to finish yesterday's homework, you can grab a couple extra sheets for yourself, okay? Before we get to the lesson, can we do a warm-up question, please? Not on your paper anywhere. It's just asking about function evaluation and then continuity. So there's a question coming up on your test that looks a lot like this. So this is a piecewise function. You have the top piece of the piecewise function is the line x plus 2, only used if x's are less than 2. And then the bottom piece of the piecewise function is a different line, only used if x's are greater than or equal to 2. I want you to evaluate it at a few spots just for fun. And then I want you to determine whether or not the function is continuous throughout its whole domain. So evaluating the function isn't too bad. You just got to make sure you're looking at the right piece of the piecewise function because of the domain. So if x equals 0, does that fall into the less than 2 or greater than 2 category? Less than 2. So you're going to be using that top blue function, and you're going to plug in a 0. So 0 plus 2, better known as 2. What about if x equals exactly 2? Yes, that would fall into this bottom category. So we're going to be plugging in or evaluating in the bottom function this time. And that would be a 5. What about if x equals 4? Is that less than 2 or greater than 2? That would be the bottom function again, greater than 2. So 2 times 4 plus 1, which is 9. And then it wants to know if it's continuous. This is the question I'm a little concerned about. Well, piecewise functions, if their pieces are polynomials, which these are, they're lines, the only place you have to look for continuity problems would be the boundary lines themselves. So what you're going to do is you're going to figure out, which I think you already kind of have, what happens at the boundary line for both of the functions. So if you plug in a 2 into the blue function, you get 2 plus 2, better known as 4. Now I know it doesn't actually exist there. We would have put an open circle if we graphed it, which we're going to do in a minute for the other problems. But I still want to know what location we're at. If you plug in a 2 into this bottom function, which you already kind of did for me, wasn't it a 5? 2 times 2 plus 1 is a 5. Here's how you can tell if they're continuous. Do they meet up? Do they match up? 4 is not 5. So is it continuous? No. There seems to be some sort of a jump or a break at x equals 2, which is the boundary line. So the pieces of the piecewise function are meeting up. I think you remember back in Algebra 2, there were some instances where, you'd have a little ray going off to the left and a little ray going off to the right, and once in a while, those open and closed circles overlapped. That would be what a continuous piecewise function looks like. They don't happen often, and sometimes they're partially continuous, like at 2, but not at 3. So there's a question coming up on your test next Tuesday, where you have to evaluate the continuity of a piecewise. Alright, it's time to graph. Today, we are going to do as much work as we can without a calculator, mostly under the premise of knowing that there's a no calculator portion of our SAT test. The other reason why we're going to do most of it without a calculator is because you can. You're PreCalc. You can do this. But we're going to use teamwork. Okay? I'm going to break up our piecewise functions into little side jobs for every piece of the classroom. I'll be like, you guys do this, and we're going to work together. It's going to be great. The first thing I want you to do, though, is if you have a highlighter or a colored pen or something, we're going to take the piecewise function and we're going to break our boundary lines with we're going to break our plane into partial planes using our boundary lines. There, that's what I'm going with. So your boundary lines are at x equals -1 and x equals 4. So I'm going to totally draw some straight lines here. They're not going to be straight at all. At -1, whoop, and at 4, so not straight. Okay. So what we've done is we've taken our entire domain and we've kind of broken it up. Something's going to happen on each of these little pieces. All right, the first piece of our piecewise function, because we're PreCalc, we're not going to see a lot of lines today, guys. They're going to be nonlinear things, typically. The first piece is the function 3x squared. Just for, memory here, guys, what does 3x squared look like? What's the shape called?
A parabola.
It's a parabola, yeah. And in particular, it would be a parabola that started at 0 and has a vertical stretch of 3. The problem is we're not graphing the entirety of the parabola. You're only allowed to graph pieces of the parabola where your x's are less than -1. So what I like to do, and they've already kind of done it for you, but you might want to do this anyways, just for the sake of process. I like you to come up with some ordered pairs. And you want more than 2, especially when you have a nonlinear function. So starting at the boundary line, which is x equals -1, what would happen if you plug in x equals -1 into this function? You'd get 3, yeah, because -1 squared is 1, 1 times 3 is 3. Now, when I go to graph the ordered pair at -1, 3, because it does not have an equal to symbol on your boundary line mark here, you have to use an open circle. It doesn't actually exist at -1, 3. So we're just going to kind of mark its placement by doing that. Now what I need from you is a series of more ordered pairs. Let's do 3 more. But you can only give me x's that are within your domain. -2. What's another one that's going to work in our
0.
domain? Well, is that less than -1?
Oh, wait, no.
Ah.
-3.
-4. Sound good to you?
-28.
Oh, you're getting crazy now. All right, let's plug in a -2. Yes, Daniel. So I have to start on the boundary line, even if it doesn't actually exist, and I mark its placement with an open circle. Because that is the limit of the top function. At -1, it's going to start switching to a different function after that. So I'm really interested in boundaries on piecewise functions. In the middle, it's important too, but the boundaries are very important. All right, so if you plug in a -2, I got a little bit of bad news for you guys. You're already up to a 12. And if you plug in a -3, you're already up to a 27.
Oh my.
And if you plug in a -4, you're up to a 48. So I got real bad news for you. You're only going to be able to plot, like, kind of fudge in -212. Now, everything off the boundary line is like a literal point, so just plot them. So this is requiring you to remember how quadratics work. What I don't want to see is your Algebra 2 brain kicking in and you draw me a ray. Is this a ray? No, children, this is a quadratic. So you're going to not do that. Okay, you're going to draw in what appears to be a curvy piece of a parabola. All right, remember you guys told me when we started that this blue piece was a quadratic function that had a vertical stretch of 3. So some piece of that quadratic is what you just drew for me. That's going to be a little nitpicky on my part. Like, I know I'm a really terrible grapher, so just do better than me and you'll be okay. Let's talk about this middle piece of the piecewise function. What does the line y equals -1 look like when you graph the line y equals -1? It's a constant function at -1, so it's just a horizontal piece. But this piece of the piecewise function only exists between x equals -1 and x equals 4. So I'm going to graph that constant piece at -1 between those two values, but you guys are going to help me determine whether I have open circle or closed circle on the boundary lines themselves.
Closed one and then open.
Closed on the -1? Why is that, Cameron?
Well,
You're right.
You see, because I kind of just looked at the graph,
Because of that?
but also because the equal to sign.
The equal to symbol indicates that we exist at -1. Very good. How about at the 4?
Open.
Open circle, and that's because it doesn't have the equal to symbol. Very good. And then there's a third piece to this piecewise function. Oh boy, who remembers what this graph looks like? It's this, yes, that's exact. Internet, you don't know. They just made a beautiful symbol for a cubic function. It looks like this. So not that. You did a way better job than that. So the wiggling component, the center of it usually is at 0, 0, but this guy's been shifted to the right 5 and up 2. So we're going to see that indicated on our graph. But instead of graphing the whole thing, let's just graph some ordered pairs that live within our domain. Starting with the boundary line. I'm always interested in about that boundary line. So for this function, it starts at 4. If y'all were to plug in a 4 here, you'd get -1 to the third power, which is -1. -1 plus 2 is 1. All right, I'm going to need some more ordered pairs from you. 5. Who else are you going to give me? Get crazy. Whoa.
Whoa.
Didn't expect 10. You did get crazy. Okay. Yeah, let's go with 7. I'm going to fall off the graph if I use 10. That's too much. It's too much. All right. So if I plug in a 5, you get 0 plus 2, which is 2. If you plug in a 6, you get 1 plus 2, which is 3. And if you plug in a 7, you get 2 to the third, so 8 plus 2, which is 10. So when I go to graph this very first point, this is my boundary line point. Are we talking open circle or closed circle on the boundary line for this green guy? Closed. All right, 4, 1, closed circle. 5, 2, regular point. 6, 3, sure. And if this is all you graphed for me, you'd probably be deceived into thinking it was a ray. But it's not. You guys told me it was a swoopy swiggle. Also known as a cubic. All right, 7. 10. There we go. Now we can see a little better picture of this. Swoopy swiggle. All right, pretend I connected. I really didn't. Notice, it's not the whole swoopy swiggle of the cubic. It is just a piece of it. Thus the name piecewise function. All right, so let's say you were lacking creativity, energy, or effort. Your calculator can help you evaluate all these pieces. And actually, your calculator can restrict the domain as well. But let's not get into that today because it's a little too exciting for us. So like on that cubic, if you're like, man, I don't want to evaluate this right now. I don't even know what it looks like. You can go to your calculator and you can type your function, that piece, into Y1. And if you go to your graph, or your table, excuse me, you just have to be careful and understand that your domain only started at x equals 4. So then you could start plotting all the points from 4 on, and then you can have all the points you want. So that's pretty nice. But you totally can do it without a calculator, right? Right, Mrs. Bruzo. We got this. We got this. We'll talk more about your calculator's capabilities later. All right, time for teamwork. Ready, team? You guys are going to talk to me about good quality ordered pairs for that top blue function in a minute. Got it? Cameron and friends, you're going to talk to me about this function in a minute. Give me some good quality ordered pairs in your domain. Taylor and friends, you get the weird one. You get this guy. I need good quality ordered pairs within its domain, please. All right, on the end, you guys are in charge of talking to me about when I have an open circle, when I have a closed circle. So I'm going to ask them about their function, and then I'm going to turn over to you and be like, open or closed circle, okay? While you're waiting for me to draw my lines, you guys might want to draw on some boundary lines. Where are your boundary lines on this problem? Yeah. Oh, man. All right, guys. Blue function, people. What kind of a shape are you going to be graphing for me, by the way? X minus 5 is a line. That's pretty boring. I'm sorry. Can you give me some good quality ordered pairs for this blue function within your domain, especially on the boundary line? 0, 5? 0, negative 5? Is that what you said? Okay. Give me one more ordered pair. It's got to be an x that's smaller than 0, so it could be anything smaller than 0. -2, -7. That's lovely. All right, I'm about to plot their original boundary line point, guys. So at 0, 5, 5 for this blue function, should I be plotting an open circle or closed circle? Talking to Sky's group over there. And it has to do with this symbol right here because it has an equal to bar. That means it does exist on the boundary line. So closed circle at 0, -5. I'm going to plot the other ordered pair that Adam gave me, -2, -7. That's just an ordered pair. And then they told me it was going to be a portion of a line, so I think I have enough information to graph a line. Boom. Got it. Killed it, didn't I? All right, Cameron's group. Ready for that green function?
Yeah.
That's another cubic function. Can you give me... It is a squiggly squiggle. Can you give me some ordered pairs within its domain? And you know what? Just give me all the ordered pairs that are integers within its domain.
1, 1.
So starting at 0.
So, 0,
0, 0.
1,
1, 1.
And 2, 8.
Beautiful. Boundary line group. When I go to plot 0, 0 for this green function in the middle, am I talking open circle or closed circle this time? Open. Very good, because it's not equal to. How about at the other endpoint for the other boundary line at 2, 8? That one's closed. Very good. So 0, 0, open circle. 1, 1, just a point. And then 2, 8, closed circle. So it's just half of your cubic function. Make sure you're not drawing me anything that resembles a line this time. This is a cubic function. A swoopy swiggle. Unofficial name. But I know what you mean. All right, red function. You guys had the weird one. It's weird. And I would expect you to use your calculator if you're like, what the heck does this look like? Because you don't have a lot of experience with this function. But you can at least give me the boundary line point. 2, when you plug that in, what do you get? And then you're like, oh, great. So then you start plugging in some more numbers that are greater than 2. What'd you come up with? Yeah, they're not great. I know. Okay, so I'll call it like 0.67, but I know what you mean. What else you get? Oh, I think you get 1/2. Yeah. Yeah. 0.5. 2 divided by 4. Yeah. So boundary line, friends, when I go to graph this first one on the boundary line at 2, open circle or closed circle this time? Open. So at 2, 1, open circle, and then I'm starting to plot these incredibly stupid points. And I'm with you, Taylor. They're not giving you much to work on. So if you even plotted more points in, what's happening is you're creating a horizontal asymptote. This is a reciprocal function. If you were to graph 2 over x, it would look like this in its entirety, where it has these 2 weird branches. And PreCalc right now, we haven't done that unit yet, so I don't expect you to have that like stored in your memory bank right now. So you would just be utilizing your calculator and some evaluation. So we're just graphing like this piece of the rational function right now, just that little piece of it. Thus the name piecewise functions. Aren't they fun?
Yeah, they're not bad.
Yeah, they're not bad? Oh. These are kind of as bad as they get for PreCalc. And what's the challenge here, guys? They're not lines anymore. Like if they were all lines, we'd be in Algebra 2 still. We got to step it up. We're PreCalc. All right, boundary lines this time. We have one at -5 and at 2. So I'm going to draw those in. Let's shake up the rules a little bit.
Can we do the open and close?
Yes, your group can be in charge of open and closed circles. Sky, your group is going to help me graph this little piece here, okay? Cameron, your group is going to give me this one. That's a nice easy break for you.
That?
Yeah, just that. It's not even a challenge for you. I'm sorry. Cheyenne and Adam, can you guys do this green one for me? All right, let me get some boundary lines in because I got nothing. That's not straight. Oh well. All right, Sky. Did your group determine what kind of shape this is? First of all, x plus 6 quantity squared. What kind of a shape are we graphing? Or what kind of a function are we graphing? His parent looks like this, if that helps you any. Well, it's not a line. Isn't it just a parabola? Yeah, it's a quadratic parabola. It's been shifted to the left 6. Keep that in mind as we go to graph things. What I'm going to need from you guys is just a whole bunch of points, starting with his boundary line point. So at -5, when you guys plug that into the blue function, what'd you get? Get a 1, yeah. And then I'm going to need some other ordered pairs. Give me like at least 4 ordered pairs within your domain, please. That'll give you a good enough visualization for what's going on. So you got to give me numbers that are less than -5. What are you going to plug in for me? Can we just go down the line? -6, -7, -8, -9? Okay, cool. This might be overkill, but you know what? It's all right. So if I plug in a -6, that gives you 0 squared. That's a 0. If I give you plug in a -7, that gives you -1 squared. That's a 1. If I plug in a -8, you get 4. Good. And if you plug in a -9, you get 9. Boundary line group. I'm about to plot a boundary line point at -5, 1. Am I talking a closed circle or open circle for this blue function?
Open.
Very good. Open circle because it's not equal to. Very good. All right, -5, 1. Open circle. Everything else is just a point. So -6, 0. -7, 1. I'm so glad you guys gave me all these points because I can really see the shape coming together now. A lot of kids get confused with where the vertex is located, and they think like whatever they plot the first time is the vertex, but that's not always the case. Like for instance here, that first point that we put an open circle at, definitely not the vertex, because we knew the vertex was at -6, 0. So the moral of the story for a parabola and all their nonlinear functions, give me lots of points. Then you won't make a silly mistake. All right, sorry to offend you, Group Cameron, but you give me the boring one, huh? Y = 7. What does that look like?
Just a line of 7.
Yeah, sorry. Hey, boundary line group. Over here at x = -5, are we talking an open circle or a closed circle? And how about the other one? Oh, man, that was super boring. I'm sorry. All right, absolute value group. Oh, I spilled the beans. It's an absolute value. Sorry. Do you remember what that shape looks like? It's a V-shaped thing, yeah. And we're only going to have a piece of it, but yeah, a V-shape. Can you give me some good ordered pairs starting with your boundary line? 2, 2. 3, 1. 4, 0. 5, 1. 6, 2. Awesome point. Ooh, that's not what you said, though. 6, 2. And notice how many points they're giving me. That's wonderful. Boundary line group. I'm about to plot a boundary line point. Open circle or closed circle? Open this time. All right, 2, 2. Open circle. All right, 3, 1. 4, 0. 5, 1. And 6, 2. And they already told me that this is a V shape because it's absolute value. But not the whole thing, obviously, because it's cut off on its domain. Nice job, group. High fives all around. That was beautiful. Piecewise functions. Oh, man. Who doesn't love piecewise functions? All right. I'm going to, I think we'll do this one. Yep, that's the last one we have. All right, let's shake it up. Who wants the boundary line question this time? All right, Cameron's group, you're going to be my boundary line people. I just gave you a weird one. Let's give you an easy one now. You ready? Can you guys do this function for me? You got this. All right, girls, can you help me with this middle function here? All right. Group on the end. You guys get the weird one this time. Square root of x plus 3. It's not that weird. Don't panic. All right. While I'm getting some boundary lines down, go find me some points, people. Oh my goodness, there's a ton of boundary lines. Wow, where are they?
-5, -2, 2, 3.
Yeah. Why they gotta set me up for failure like this? This is awful. All right, so this is a very unusual piecewise function. This is one where like the pieces definitely aren't going to be continuous. There's going to be whole entire boundaries where there's nothing. So it happens. It's okay. All right. What'd you guys come up with for y equals 4? What kind of a shape are we looking at? It's a line. Yeah, a horizontal line at 4. So where are we at here? So right here, continuing on to the left. All right, boundary line group. When we hit the boundary line at -5, am I supposed to? Okay, open circle. And that's because of this is not being equal to. Very good. All right, group in the middle. X to the 3rd power. You have a cubic function, which the entirety of a cubic function looks like this, but you're not graphing the whole thing for me. So be careful. You're jumping to the -2 to 2 region. So it would be smart if you guys just give me every integer between -2 and 2. That would be brilliant. -2, -8, cool. Uh-huh. Yeah. 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 All right, boundary line crew. When I go to plot the -2 x value on that first boundary line, are we talking open circle or closed circle? Closed. How about the other boundary line for that one? 2 closed circles? That's weird. All right, -2, -8, closed circle. Same thing with +2, +8. Here we go. -1, -1, 0, 0, 1, 1. Thank you for all those points, because now I can see that cubic really shaping up. Yeah. That was almost perfect. Kind of got a little weird at the end there, but so close. All right. Now, my friends with the weird one. You're jumping all the way over to x equals 3 for the start of your domain. So, do you guys remember what this function looks like, this green function, when it's a square root function, like what the basic shape of it is? That's exactly right, Brandon. It's half of a sideways parabola. It's going to be one of these. And this one in particular has been shifted left 3. So, you're going to see a piece of it. Start telling me some ordered pairs for this green one. Starting at 3. Yeah, and you should be going, right away because it's gross. What happens when you plug in a 3? You get square root of 6. Since I have to graph, give me a decimal. Is it 2.2-ish? I don't know. I don't like hand deriving square roots, guys. I can only estimate. Last class lied to me. I said it was 2.2. Liars. All right. 3. I'm about to plot a point at 3, 2.4. It's on the boundary line. Cameron's group. Open circle or closed circle?
Open.
Open this time. All right. Yeah, I called you out first hour. You're lying to me. All right, guys, give me a little nicer ordered pair this time. Something that I wouldn't mind plugging in and creating a nice square root. 6 would be beautiful. 6 plus 3 is 9. Square root of 9 is trace. So 6, 3. And then we know enough about square roots from Brandon's description to be able to kind of fudge in a weird sideways half of a parabola. Beautiful. That's perfect. Nice job, guys. Could you all look at your Piecewise packet real quick? And I want you to turn to the second page, the first page, second side. We put some review questions about average rate of change on there, which I didn't want to confuse you. Some kids looking at that like, wait, you didn't talk about average rate of change today. I know, it's old. So when you're looking at the Piecewise packet, numbers 7 to 10, I think, the average rate of change questions. So let's look at number 7. They give you a function. And then it gives you an interval from 0 to 1. This is an x, it's like a domain interval. So they want to know the rate of change from x equals 0 to x equals 1. So what y'all need to do for me, is you need to figure out your ordered pairs when x equals 0 and when x equals 1. So that's just a matter of you plugging them in. So plug in a 0, you get a 2. And then plugging in a 1, let's see, you get 2 plus 2 plus 2, which is 8. But this was, remember on the last test, some of you forgot to like do this last step. Now you have to find the average rate of change. Remember, it's just slope. So you're going to find 8 minus 2 over 1 minus 0. So that'd be a 4. So those questions right there are just kind of reinforcing the topic of average rate of change because it does show up on your next test. It really has nothing to do with your piecewise function practice. We just threw them in there. Oh, that's not 4. Gosh, be golly. That's 6. I quit. You know what happened? I said it was 4 during first hour too. First hour. What is wrong with you guys? That's rude. It's me. I'm the problem. You know, I told you they're quiet. They're so quiet they can't even tell me when I'm stupid. Maybe they're just polite. Maybe that's it. All right, guys. So for homework, you have... I would start this packet. I would do the first page. I think that would be brilliant because you're all ready to do that first page. And then you have 4 problems out of the textbook that you can do that you're going to do on graph paper. It's all piecewise, okay? Graph and piecewise, except for those couple of rate of change questions. Hopefully you're catching on to the homework and you're keeping up with it because I told you last night was a beast, right? That was a big homework assignment. Well, you're going to have a lot of weekend homework, mister. Oh, Cameron. So the homework assignment, that was... We're up to the piecewise packet in your homework checklist, okay? We're almost done. You have one more, it looks like. Okay.